Alright, welcome everybody, and we're here to discuss Kirchhoff's rules. Kirchhoff's rules are a set of rules to help us solve what's going on in more complicated circuits. Right? Specifically, when we have possibly multiple systems linked in parallel, how much current is running through every resistor that we see. Alright, so the key with Kirchhoff's rules, there are two rules, by the way. But first, before we get into that, we need a circuit, right? So in the circuit, we have to have at least one power supply and some resistors, right? So let's put in a power supply, and then let's give it some resistors, right? So I'm going to have those, and then I'm going to add on to this branch here, right? So we have three resistors. We'll call them just R1, R2, and R3. And then we have our power supply, which has some voltage in it, V. Alright, so for Kirchhoff's rules, again, we have two rules. The first one is our voltage rule. Right, so there's Kirchhoff's voltage rule. What the heck is the voltage rule? Well, it's a statement on, well, voltage, right? Clearly. The key here is when we go around one complete loop, the total voltage additions and subtractions that we experience must be zero. All right, and the reason for this is because we know voltage stems from a path-independent quantity, right? Potential energy divided by Q gives us our voltage. And since potential energy is path-independent, that means our voltage is path-independent, which means if we start and end at the same spot, our total change in voltage must be zero. Right, this is the same as if you leave your house. Right, if I step out of my front door and I decide to walk around my block. As I walk around my block, I might go a little bit downhill and I might go a little bit uphill. But when I get back to my front door, I'm going to be at the same elevation as when I started. Right, my net change in elevation will be zero. The same is true for voltage, right? Because again, we can think of voltage like hills, right? So as we leave and we go around, we're going to go downhill and we're going to go uphill. But when we get back, we're going to be at the same elevation that we started at. We have to be. It'd be really weird if I left my house, walked around the block, and came back and I was 10 feet higher than where I started, right? That does not happen. So as we go around a loop, our net voltage must be zero when we get back to where we start. Importantly, this requires a loop, right? You have to have a loop. Now, here's where things get tricky with Kirchhoff's voltage rule. You have to pick directions, right? How do you know whether you're going uphill or downhill? Right, so the key is we have rules for voltages and then we have rules for resistors. All right, first let's talk about our resistors because they're the more complicated one. For resistors, whether you are going uphill or downhill depends on the direction of your current, right? Because importantly, current, that's our charges. And remember, if voltage is a hill, current is like the water going downhill, right? So our water always goes downhill. What this means is we just pick a direction. Now, importantly, for this step, when you are picking a direction for your current, it does not matter which way you think it goes. Right? The math will always tell you if you were right or wrong, right? If you pick the direction the current actually goes, your answer will be positive. If it turns out the current goes the other direction, your answer will just be negative because current is a vector, right? So I'm just going to say I've got a current coming this way. I will call that I1. Now, importantly, the reason I'm calling this I1 and not just I means there must be other currents. As we go down, we see right here there is a split. Right? This split means some current will go this way and some current will go this way. So I can say, all right, there's some current I2 here and some current I3 going through this branch. All right, so we have to pick directions for our current. Once we have those directions, then we can determine what's going on. Right? So once we have directions for our current, we pick loops. Right, we have to have a certain number of loops for our voltage rule to work. Now, I just want to illustrate this with one loop, and then we'll talk about how many loops you actually need. All right, so I'm just going to pick a loop. Let's pick this loop right here. Now notice I am denoting the direction we are going around this loop. That is very important, right? When you leave your house, are you going right or are you going left? That determines if you first go uphill or if you first go downhill. All right, so we have to pick a direction for our loop. And then we need a starting point. I always like to start by batteries. It's just easier for me. So I'm going to start right here at this corner. And then I'm going to go around this loop. All right, as I get to this power supply, this voltage, right, this voltage is either going to be a positive voltage or a negative voltage. Which one it is depends on which way my loop goes, right? So voltages, their direction, right, their positive or negativeness is determined entirely by the direction we go around this loop. I am going down through this, which means I'm going from negative to positive. So I'm starting at the bottom of the hill and I'm going up, right? Because this is my positive side of my battery, I am increasing my voltage, which means for this loop, V is positive. And then I come down here and I have to go through this resistor. So then the question is our voltage drop across the resistor positive or negative? Well, importantly, my loop is going in the same direction as my current. Which way does current flow? Downhill. If I am walking and I notice that there's a stream next to me, and I notice I'm walking in the same direction as the stream, I must be going downhill, which means I'm going from a large voltage to a smaller voltage. That means this is negative. So this is going to be minus the voltage in resistor 1. And then I'm going to come through resistor 2, right? I have to complete my loop. I have to start and end at this location. So I'm going to go up through this. Again, my current is pointing in the same direction as I am traveling, which means this is minus the voltage that is in resistor 2. And then I come here, there's no resistors or voltage supplies here, so then I just get back to where I started, which means this must equal 0. Now importantly, right, because what we're actually trying to find are these currents. So I need a way to relate these voltages to these currents. That's where Ohm's law comes in, right? For Ohm's law we know V equals IR. So this really is just V minus I1 R1 minus I2 R2 equals 0. So this is the equation for our loop. Right, so that's how we use Kirchhoff's voltage rule. Right, importantly, before we go on, I do want to point out we can do it for this loop as well, or this bigger loop. Right, so if I look here, I can go around this loop. And let's say I go around this loop that way. Now there are no power supplies, right? There's no voltage sources in this small loop, only resistors. So I'm just going to start right here. If I start at this corner, as I go down through this resistor, right, my direction is opposite that of my current. Again, if we think about current like a stream, as I'm walking, right, water is flowing downhill, I am going opposite that direction, which means I must be going uphill. So when I go through this resistor, this is a positive voltage. So that's going to give us I3R3, right, because we know V equals IR. So this is a positive voltage. And then I'm going to come over and I'm going to go up through resistor 2. I'm going up, my current is going up. If I'm going in the same direction as my current, that gives me a negative sign. So this is going to be minus I2R2. And then I'm back to where I started. So this equals 0. So that's another equation that we can use. And again, you could also make one big loop here. There are 3 possible loops in this geometry. But I want to point out you don't need all 3 loops, right? Now, of course, we need 3 equations, right? How many unknowns are there? 1, 2, 3. So we have 3 unknowns, which means we need 3 equations. So we still need one. You could use the loop. But there's a better option, and that is our junction or current rule. Let's just call it the current rule. Right, so our Kirchhoff's current rule. Okay, so what the heck is Kirchhoff's current rule? Kirchhoff's current rule is just conservation of charge. That's it. That's what it is. It's just telling us charge must be conserved. Well, importantly, conservation of charge also means conservation of current, because current is just moving charge. So if we're saying our charge has to be conserved, our current has to be conserved. What this means is I can look at a junction, right? I can look at some small subset of this thing. Now, of course, what does a junction mean? We can get complicated with that, and we'll talk more about that in lecture. For now, a junction is just wherever these things meet. So right here is a junction. And so Kirchhoff's current rule just tells us if we take all of the current coming into the junction, this must equal all of the current coming out of the junction. So if this is our junction, we see a current coming in, right? I1 enters this blue circle. So the sum of our currents coming in is I1. Leaving this blue circle is I2 and I3. So when we take everything going out, it is going to be I2 plus I3. And so this gives us a third equation. Importantly, anytime you can use the current rule, you want to use the current rule, because this equation is significantly easier than these two, right? It immediately tells us I1 is just I2 plus I3. So that means when we come over to this equation, this I1 is just I2 plus I3, which means then we have two equations with two unknowns, I2 and I3, and we can solve that. Right, so that is the key behind Kirchhoff's rules, is we have a current rule and a voltage rule. All right, so with that in mind, let's do a let's do a bit more complicated of an example. All right, so let's circle that up and delete it, and then let's come up with a more complicated looking loop. All right, so I can have a power supply, right? Have to have at least one of those. And we're going to come over and go through a resistor, and we're going to come up and go through a resistor, and we're going to have another power supply, and then we're going to go back to where we started. And then we're going to give this another option. We're going to say, oh, it can go over here and through this power supply and get back to where we started. All right, so we have this more complicated circuit where we have 3 resistors and 3 power supplies. And we have to figure out what the heck is going on here. Now, if we want to use Kirchhoff's rules, the first thing we need to do is determine how many currents are in this circuit. All right, because that tells us how many unknowns we have. Well, if we look at this, throughout this entire section here, we are going to have one current. So we have a current 1 that I'm going to say goes this way. Again, it does not matter which way you say current 1 goes. If you're wrong, the math will tell you. So we have a current here. Then when we hit here, that current splits off into 2 possible directions. It can either go this way or this way. And so, anytime you have a split, you get new currents. So this is going to be current 2, and this is going to be current 3. So this is so far looking a lot like the last example, right? Because we have a branch and it splits off into 2 branches. We just happen to have an extra power supply thrown in here. Now that we know what currents we have, I always recommend using the current rule next. We want to pick a junction and say, all right, how much current is going into that junction? How much current is leaving that junction? Let's pick this junction. All right, so we can say, all right, current into this junction must equal current out of this junction. All right, well, entering this junction, we have I2 and I3. So we have I2 plus I3 must equal however much current is leaving this junction, which is I1. So there is one equation out of the way. Well, we need two more. To get the other two equations, we use the Kirchhoff's voltage rule. So we have to pick loops. Now, how many loops do we need to pick is based off of how many unknowns do we have. Right? Because remember, to solve a system of equations, you have to have the exact same number of unknowns as you do equations. Right? You have to have a square system. So we have 3 unknowns, which means we need 3 equations. Importantly, we already have 1 equation, so we need 2 more. So we need 2 loops. And again, you can pick any 2 loops. So I'm going to pick, which one do I want to pick? Right, there's 3 options. You can pick any 2 of the 3. Let's pick that one. That will be, we'll call it loop 1. Right, so for loop 1, we have to have a starting point. Like I said, I like starting before we go through a voltage source. So I'm going to start right there. My loop goes up through this power supply. As I go up, I'm going from the positive end to the negative end. Well, if I'm going positive to negative, I must be going downhill. Now, of course, I'm realizing we didn't give any of these any names, so we'll call this V1, V2, and V3, and R1, R2, and R3. So we're going up through V3, which means we're going from positive to negative, so we get a negative V3. Then we have to pass through our resistor. Our current is going in the same direction as our loop. Anytime your current and loop are in the same direction, it is negative. So this is going to be minus I3R3. Then we hit this junction and we're going to go down through V2. Again, if we're going down, that means we're going from positive to negative. So this is going to be minus V2. And then we're going to go down through R2. We're going down, but I2 goes up. If I2 is going up, but we're going down, we're going in the opposite direction, which is a positive. So this is going to be plus I2, R2. And then we're back to where we started, so this must equal 0. So there's our second equation. And then we just need one more equation, so we need one more loop. All right, so why don't we pick the big loop? Right, so this is going to be loop 2. It is all the way around the outer perimeter of this thing. Again, we need a starting point. I'm going to start right there. So if I start here, I'm going to go down through V1, going from negative to positive, which means this is positive V1. And then I'm going to pass through the resistor. My loop and my current are going in the same direction, which is a minus I1, R1. And then I'm going to come over here, and I have to go up through V3. We already went up through V3. We know that's a negative. So this is minus V3. And then over through R3. Again, our loop and our current are in the same direction. So that's minus I3, R3. And then we're back to where we started. So this must equal 0. Now we have a set of 3 equations. So all we have to do is solve these 3 equations. Right? Again, this one already tells us what I1 is. So this equation is really V1 minus I2 plus I3 times R1. minus V3 minus I3R3. Now, I'm not actually going to solve these because it's actually more annoying to solve these without numbers. It's one of the few times I want numbers in my math, is when I'm dealing with more than 2 equations, right? In things like this, it's just a lot easier to work with the math as opposed to just pure variables. All right, but this is how we get those 3 equations, and then you just have to solve them. So again, this is how we can use Kirchhoff's rules. If you want a step-by-step system, step number 1 is how many currents and which way do they go? Importantly, when we're asking which way do they go, just pick, right? It does not matter which way you think they're going. The math will tell you if you're right. So you just have to pick a direction for your currents, right? So again, the first thing you need to do, how many currents do we actually have, and which way are they going? That is step 1. Step 2, pick a junction. And use the current rule so that you can write down an equation. All right, that gives us our first equation, is Kirchhoff's current rule. That comes from picking a junction. All right, so that's step 2. Get the easiest equation you can. Step 3, you need to pick loops. All right, so pick loops. How many loops? Enough to complete your system. Right, so in this case, we needed 2 loops because we need a grand total of 3 equations for our 3 unknowns. If instead we had 4 currents, then we would need 4 equations. 5 currents, 5 equations, so on and so forth. Remember, we need as many equations as we have unknowns. All right, so step 3 is just pick loops. Pick whichever loops you want, as long as they start and end at the same spot, right? So it has to be a complete loop. So if we go that loop, or this loop, or this bigger loop, right? Doesn't matter. Pick however many you want, right? Well, pick whichever ones you want. How many is determined by our system of equations, right? So step 3 is pick loops. Step 4 is our voltage rule, right? Use these loops to write down these equations. And remember direction, right? So when we're using the voltage rule, if you are going from a small end to a big end of a battery, right? If we are going in this direction, then that is a positive V. But if you were going the opposite direction, that is a negative V. And for a resistor, right? If we have to pass through a resistor, if our current goes this way, but our loop goes opposite it, I guess I should use the same colors, right? So this is our loop, this is our current. This would be a positive, because we're going opposite the direction of our current. So this would be IR. If, however, our loop were going in the same direction as our current, right? If you're going in the same direction, loop and current, that is going to be a negative IR. And remember, when you get back to where you started, it must equal 0. Right? So follow these steps, and you can do really any Kirchhoff's rule problem. Right? You can do some very complicated circuits just by following these steps. All right? So that is our brief overview of Kirchhoff's rules to help prepare you for your lab on Friday. Right? And of course, we will talk about this more in class, and we'll actually, we'll do this more in depth. right? Again, there's some nuances with junctions that we can use to our advantage. And of course, which junctions should we pick? Which loops might be easiest? Those are things we're going to talk about in lecture. And of course, we're also going to deal with more complicated circuits. But in the meantime, this should at least help prepare you for your lab. All right, so I hope that made sense. And of course, if you have any questions regarding this, please let me know so that we can help solve those either before your lab, during your lab, or following your lab. But otherwise, take care.